So we're going to look a little bit at the work of Faraday and Lenz in terms of electromagnetic induction. Now, electromagnetic induction is all about having a loop or coils of wire inside of a magnetic field, maybe something that looks like this. And as we have the little coil inside the magnetic field, there is flux going through it. And of course, magnetic flux would be equal to BA cos theta. And actually produce electricity, the whole idea is to take that flux and change it. And that's the key for creating induced currents and creating electricity using electromagnetic induction. Now, for the different factors, of course, magnetic field strength is really, really important. The area of the coil is really important because that's how much flux can actually go through it. The bigger the area, the more flux can go through. But one of the trickier ones is the cos theta. Because a lot of people would think and look at the picture and say the angle is 90 degrees. Well, cos of 90 degrees is 0. That would mean that there's no flux through the coil. But that doesn't make any sense because just looking at the picture, you can see there's lots of flux going through it. And that's because the angle isn't measured between the coil and the field. It's actually measured between the normal to the coil and the field. And that little angle right there is 0 degrees because they're parallel. So you got to be a little bit careful because that angle right there is between the normal to the area and the actual magnetic field itself. And of course, in this diagram, the angle would be 0 degrees, and the cos of 0 degrees, of course, is 1, which means there's maximum flux. And this picture definitely has maximum flux going through it. So when you actually induce the EMF, we have the good old EMF expression, induced EMF is equal to negative N delta phi B divided by delta T. And of course, what they figured out is it's not just about changing the flux, it's also about how quickly it occurs. So the faster you change the flux, the more induced EMF you can have, but also increasing the number of loops of wires also really beneficial. So it's not just about changing the field or the area, it also involves how many coils you have and how quickly you do it. Now, of all the things you can change, probably the easiest thing to change would be the angle. And that's why in generators, they have it spinning all the time. So when they're spinning, the B can stay the same, the A can stay the same, but the theta is consistently changing, so you have a continually changing EMF and producing electricity for you to actually use. Now, it could be other things beside the angle changing. I mean, if we expand out the expression, we've got negative N BA cos theta divided by delta T. That delta that's over here could apply to any one of these things. You can change the field, you can change the area, you can change the theta. You can change any one of those things to actually produce an EMF, but the angle, of course, would be the easiest thing to change just by spinning the coils of wire, like again in a generator. Now, the other part of this that they sort of figured out is when you actually do induce an EMF, another magnetic field is also produced. So suppose we've got a magnetic field, something like that. Let's put a coil inside of there, something like this. Okay, so there's our coil. Right now, that coil has a magnetic field going through it. Now, what if instead we took that coil and we removed it from the magnetic field? Well, if you remove it from the field, you will actually have a change in flux. And if you have a change in flux, you can then induce an EMF. What they figured out is when you actually do this, another magnetic field can actually be produced as well. So when you actually produce the second magnetic field and induce a current in there, it'll sort of try and undo what was done. It's sort of like giving vegetables to a 4-year-old. If you try and give vegetables to a 4-year-old, they'll try and push back and say, no, no, no. But if you try and take candy away from a 4-year-old, they'll try and get it back. Well, induction sort of works the exact same way. They often try to undo what was done. So in this case, when we took the coil out, it lost the magnetic field symbolized by X's. So since it lost X's, what it'll do to compensate is it'll actually make its own X's. So the induced magnetic field would actually be an X inside of the coil while the induction is taking place. And to do this, it'll actually produce an induced current going in that direction. And if you took that coil and then put it back into the field, you would get the exact opposite result. You are now giving it X's, so what it'll do is it'll try to make dots in order to actually cancel off the field you're giving it, and the induced current would go in the opposite direction. Another scenario might be a little bit different. Maybe you have a magnetic field that looks something like this. And again, we can put a coil inside of there, something like this. And of course, there is flux going through it. Well, let's look at another scenario. What we could do. Maybe somehow we make the magnetic field weaker. Well, if we make the magnetic field weaker, well, inside the coil, it's going to lose a magnetic field going towards the right. So what the coil will do is it would actually make a magnetic field going to the right. And it would actually create an induced magnetic field that would look like this to try and compensate for the field that it's losing while the initial magnetic field is becoming weaker. And this has a lot to do with Lenz's law and that type of stuff, where a secondary magnetic field and a secondary current are going to be produced, which are going to try and cancel off the change that is occurring with the initial flux and magnetic field.